Hello. Today we're in this section or in this video, I'll go over the four main types of discontinuity. So there's pretty much four types of discontinuities. The first one is called the jump discontinuity. It occurs when the curve breaks at a particular place. In other words, this limit of x approaches a to the left of f of x is not equal to the limit of x approaches a to the right of f of x. So this is what are the related one-sided limit. So yeah, so usually this is gonna you're gonna deal with this one on piecewise functions. So notice that what's the limit? The limit of x approaches a to the left is this value, and the limit of a approaches right as a approaches to the right is this value. There are two different values, so that's why this is discontinuity. And as you can see, you also picked up your pencil, so that's how you know it's discontinuous. Okay, so the other one is point discontinuity. Occurs when the curve has a hole in it from a missing point because the function has a value at that point that is off the curve. For in other words, as the limit of x approaches a of f of x does not equal f of a. So when you plug in f of a, it's not going to be the same as your limit, right? So f of a, when you plug in f of a, it's this y value, and then the limit is obviously this value. So as you can see, they're not equal. And it looks, yeah, it looks like you didn't pick up your pencil, but when you had to draw that dark circle, you did have to pick up your pencil. That's why it's discontinuous. Okay, so and then the third discontinuity is the essential discontinuity. Occurs when the curve has a vertical asymptote. So yeah, vertical asymptote is dealing with rational functions. So you're probably going to deal with rational functions with essential discontinuity. So as you can see, this has a vertical asymptote of this value, and then this has a vertical asymptote. So essential discontinuity is dealing with rational function. And then the fourth one is the removable and non-removable discontinuity. So when you're dealing with removable and non-removable discontinuity, you're most likely dealing with rational functions. How I like to think of removable discontinuity is this removable discontinuity is the whole. So it's the one that could cancel. So if you go back to your algebra course, you know you have a whole of rational function when something cancels. And the non-removable discontinuity would be the vertical asymptote after canceling the common factor. So let's look at an example. We have f of x equals x minus 3. This is a rational function, x minus 3, x minus 5, x minus 1, x minus 5. As you can see, the x minus 5's cancel. You have a whole at x equals 5. So that whole is so you have a removable discontinuity at x equals positive 5. Why is it positive 5? Because if you set the one that cancels x minus 5 to 0, and then you solve for x, you get 5. Okay. And then you have a non-removable discontinuity at x equals to positive 1, because when you cancel it, you have a vertical asymptote at x equals 1, right? You have this. So maybe it's a good idea to show you how it would look like. So if you were to graph this rational function, so you know you have a whole at x equals 5. And our new function, after we cancel the x minus 5, it's going to be x minus 3 over x minus 1, right? And then let's find the y value of the whole. So to do that, you plug in 5 into the function. So that's 5 minus 3, and then 5 minus 1. So that's 2. And then 5 minus 1 is 4. So you have a whole at, this could be reduced by 2. So you have a whole at a y value of 1/4. So you have a whole at x value of 5, 1/4. And then you have a vertical asymptote at x equals +1, because to find your vertical asymptote, you set the denominator to 0. So in our case, our denominator is x minus 1. Set it to 0 and then solve for x. Okay, so let's kind of graph it to see, to give you an idea of what why it's removable and why it's non-removable. So we have a removable at x equals 5 and a non-removable at x equals +1. Okay, so we have one at our vertical asymptote is at x equals 1 right here. And then we have a horizontal asymptote at y equals 1. Why? Because on the numerator, our numerator, our highest degree is x1. And then on our denominator, our highest degree is x1 as well. So when the degrees are the same, it's the coefficient. So this has a coefficient 1, this has a coefficient 1. So that's why it's 1. Okay, and then you have a whole at 5, 1/4. 1/4 is about 0.25. Here's 1, so 0.25 right here. So open circle. So the good news about the whole is that we know we don't have to plot any points because we know our graph is going to look like this. So we know that the right side is going to look like this because of this hole. And then we got to pick up, then we got to test the point what the left side look like. So we can't, so we're going to test an x value, and we can't use our vertical asymptote to put 1. So we can use 0, -1, -2, etc. So let's do -1. So we're going to put it into this new function, our new one. So that'd be -1 minus 3, -1 minus 2. I mean, -1 minus 1. That's -4. -1 minus 1 is -2. So that's +2. So the point here would be at -1, 2. So it would be right here. So this is enough information because you know that it won't cross this asymptote and it won't go below this asymptote. So like this. Okay, so that is what the graph would look like. So just remember, removable discontinuity is the whole, the x value of the whole, and then non-removable is usually it's going to be the vertical asymptote of your after canceling the whole. Okay, so in the next section, we're going to go over problems involving continuous and discontinuity.